guys, so in this video we'll be covering exponential functions, and this is part of the IB Math AA, HL and SL course. And so in this video we'll be covering exponential functions and their graphs, as well as logarithmic functions and their graphs. So an exponential function is something that looks like the graph I've roughly drawn on the left, and we can define an exponential function with a function with a positive constant other than 1 raised to a variable exponent. So an example would be 4 to the power of 2x or e to the power of x by 2. The base, which is 4 or e in this case, can be denoted as a, and this would always be a constant, and the variable would always have, the exponent would always have the variable, which would be x. And this works if a has to be greater than 0, and it cannot be 1 because 1 raised to any power would still be 1. Okay, so here are a few important things we need to know about an exponential function. So an exponential function that has, let's say, f of x is a to the power of x, where a is greater than 0. So this would have a domain that's from negative infinity to infinity, a range of 0 to infinity, and the y-intercept would be 0, 1. And now if a is greater than 1, then f is a growing exponential function and it continuously increases. And so the x-axis is a horizontal asymptote. That x approaches negative infinity when a to the power of x approaches 0 from the right side. And finally, if a is between 0 and 1, then f is a decreasing function, and it continuously decreases. And the x-axis is a horizontal asymptote when x approaches infinity from the positive side, and when a to the power of x approaches 0. So what that means is, let me draw a small little graph just here. This basically is saying that the exponential function will have a horizontal asymptote on the horizontal axis. So the function would kind of look like this, meaning it would come really close to the asymptote but never actually touch. And this one is increasing, and a decreasing one would just look the exact opposite. And it will go on to like infinity. Yeah, so I hope that makes sense. Okay, so let's look at this image really quickly. It shows us a bunch of exponential functions, and we need to notice the following in this graph, like in these graphs. So when a is bigger than 1, the graph is positive and increasing for the entire domain 0 to infinity. So that means when a is positive when a is greater than 1, meaning 2, 3, 4, 5. That includes this yellow function, the blue one, brown one. These are all increasing for the entire domain of the function. As x increases, the graph is getting steeper and steeper and steeper. Another thing we can say is f of x is equal to a of x, which is equal to 1 over a to the negative x. And so the graph of y equals to a to the negative x, this is a reflection of y equals a to the x in the y-axis. And we can see that in this image. So this is 4 to the negative x, which is the same as 1 over 4 to the x, which is a reflection of the yellow function in the y-axis. Same for the green and blue, and same for the pink and brown. So if we have it to the negative power, it just reflects in the y-axis. So now we can move on to exponential modeling, and this is basically exponential growth or decay, which is the application of exponential functions in real life. And this is mainly in terms of interest rates, so either compound interest or simple interest. And so let's say we have a principal amount. Let's say we have a principal amount P, and the annual interest rate is R, and it's compounded once a year. If the interest is added to the principal at the end of the year, the new balance P1 would be equal to P plus PR, right? Because P is the principal amount, and then the annual interest rate is R. So P plus P times R would be at the, what would be their, amount at the end of the year. And we can write this as P times 1 plus R. And so the pattern of multiplying the previous principal by 1 plus R is repeated in each successive year. So let's take a look at what I mean. So this is at the end of year 1. Right? So at the end of year 2, P2, we would have P1, 1 plus R, and P1 was P times 1 plus R, so that would be P times 1 plus R times 1 plus R, so that would be at the end of year 2. P3 would basically be P2 times 1 plus R, which would be P times 1 plus R, 1 plus R, plus R, and this would be at end of year 3, and it goes so on, so on, so on. So PT would be P times 1 plus R to the power T, because we can notice that over here that we have at the end of third year, so we have 1 plus R 3 times. At the end of second year, 1 plus R is 2 times. At the end of first year, 1 plus R is just 1 time. So that's the pattern we have. And so basically this T is when it's compounded once a year, right? So we can just keep it as 1, 2, 3. At the end of year 3, T would be 3. At the end of year 2, T would be 2. But if we need to model more frequent compounding periods of interest, let's say we need to compound them quarterly, monthly, or daily, we need N to be the number of compounding periods per year, and let T be the number of years. Then the rate per compounding will become R over N, and the account balance after T years, let's write it up here. The account balance after T years, when you compound more frequently, would be P times 1 plus R over N times T. This is kind of our golden formula for any interest question. where t is the number of years and n is the frequency of compounding the interest. And so the reason we have r over n once again is because the rate per compounding would become r divided by n, because r is for per year, and if we're compounding more than once in a year, it will obviously be r divided by n. N is how many times a year, basically. So if it's every month, then n would be 12. If it's quarterly, n would be 4, so and so. And the annual interest rate, r, must be a decimal in this case. We can't leave it as a percentage. So if they give you like 9%, you need to write it as 0.09. Okay, let's have a look at this example. So we have Hugo deposits $900 into an account that pays 4.55% interest per annum, which is the same thing as per year. So part A of the question is, how much money will Hugo have in the account to the nearest cent at the end of 5 years if the interest is compounded monthly? And part B is, how long will it take Hugo to double his money? Okay, so let's work with part A first. And so the first step we have to do is substitute into this formula that I have written in blue here. And so this would give us A is equal to 900, which is the principal amount, meaning the amount that he initially deposited, times 1 plus rate of interest in decimal, would be 0.0455, divided by n, which is how many times a year it's compounded, and it says monthly, so that would be 12, and then to the power of 12 times 5, because it's asking at the end of 5 years. And if we solve this, we would get A as 1129.425695, but the question specifically says to round it to the nearest cent, which would give us 1129.43. We just solve it from our calculator. It's as simple as that. Now part B. Part B is a little bit more lengthy. So we need to figure out how many months it will take for Hugo's money to be doubled. So it's 900, and we basically need it to be 1800. And we need to find the amount of time it's going to take. So we can still form an equation using the formula. So what we know is the end result, which is A, needs to be 1800. The principal amount was still 900. The rate of interest still stays the same, and so does the amount of times that it's compounded. But we need to find x, which is the time it takes for it to reach 1800. So now what we can do is simplify the equation, divide by 900. It will give us 2 is equal to 1 plus 0.455 by 12 to the power of x. We can take the natural log of each side. So we can take ln of 2 is equal to x ln of 1 plus 0.455, 0.0455. And it's going to be 0 there too, over 12. And the x comes in front because it would be as an exponent here, and we know from the laws of logarithm that if we have an exponent in the log, it can just come in front of the expression. And now we can just solve for x by dividing. And so the x would equal to ln of 2 divided by ln of 1 plus 0.0455 by 12. This would cancel out, and we would have x is equal to 183.2, which is saying 184 months and if you want to calculate it, that would be 15 years and 4 months. So it would take a long time for him to just double his money. And this is basically it for exponential functions. The questions are more or less the same. It's either about rate of interest or radioactive decay, but the pattern is pretty similar, as long as we know that an exponential function is when the base is a constant and the exponent is a variable. We can do almost any question. Okay, now we can have a look at logarithmic functions, and logarithms and exponentials kind of go together. We've already seen and we already know that if 2 to the power of 3 is equal to 8, then log base 2 of 8 is equal to 3, right? So in general, what we can say is if ax is equal to b, then x is equal to log a of b. And we can say that logarithm is kind of a tool that helps us evaluate the unknown exponent of a known power. So in terms of functions, we can see that exponential and logarithmic functions are also related in kind of an interesting way. Okay, now let's have a look at this graph on the left. And this basically shows us what I meant by that interesting relationship between logarithmic and exponential functions. Over here, we can see that the pink graph is log 1.07 of x, and the blue graph is 1.07 to the power of x. So the blue one is clearly the exponential function because, again, the exponent is the variable. And we can see that the pink one is a logarithmic function. But what do we notice about them? That they are the inverse of each other because they're reflected in the line y equals to x. Important thing we need to note is that y equals to a of x and y is equal to log a of x are inverse of each other. Now, if you don't know what an inverse function is, we do have a whole video on that, so you can go watch that video if you have no clue what an inverse function is. But basically, we know that the inverse function is a function that reverses another one. So if the function f is applied to an input x and gives a result of y, then applying its inverse function to g, inverse function g to y gives a result x. So basically the domain and range of the two functions switch. And that's what's happening between exponential and logarithmic functions. So we can also say that a logarithmic function is mapping x approaches log a of x with the continuous domain x is greater than 0 and range from negative infinity to positive infinity. And for log ax, so for the logarithmic function, which is this one, we have a vertical asymptote at x is equal to 0, and we can see that the pink graph never really touches it. And this is where log ax approaches negative infinity as x approaches 0. Now let's have a look at this graph. We can basically see the different types of logarithmic functions. And what we can notice is that all functions, so the pink, blue, and orange one, go through the point 1, 0. So as the logarithmic and exponential functions are each other's inverse functions, it's automatically implied that log a of x is equal to x and a to the power of log base ax is equal to x. And if log ax is equal to log ay, then x is equal to y, which makes sense because we can kind of just cancel out the logs. But only in this case. But again, something interesting is that all these logarithmic functions go through the point 1, 0. So this is all we need to know for this video. I hope this helped you guys, and yeah, thank you.